If you have a smartphone nearby right now, I mean, I want you to just pick it up, just the whole in the palm of your hand for a second.
Yeah, really feel its weight.
Exactly. Feel the weight. Because it comes in at about 170 grams, which is roughly the weight of a common sparrow.
A sparrow. That's a great comparison.
Right. It's small, it's light, it just sits in your pocket. But that little rectangle connects 9 out of every 10 people alive today.
Which is just staggering when you think about it.
It really is. There are over 7.5 billion active smartphones on the planet right this second.
And you could argue it's the fastest, the most widespread adoption of any technology in human history.
Oh, absolutely. And yet we treat it like magic.
Yeah.
We really do. We treat our phones like these, black boxes that just magically appear on a store shelf.
Yeah, you buy it, you charge it, you swipe on it.
And then you replace it when it breaks, right, without ever really thinking about how it actually got there.
We all do it.
So today, our mission in this deep dive is to just completely strip away that illusion. We're looking at a fascinating visualization and reading by 𝗏𝗏𝗺, assisted by Claude Sonnet 4.6, titled "The Rectangle in Your Pocket," a coexistence reading of the smartphone.
It's a brilliant piece of work.
It really is. And the goal here is to reveal that this phone is not just a consumer product. It is literally the most intricate, massive act of human cooperation ever attempted.
Yeah, and there's this ancient Sanskrit concept mentioned in the source that frames this perfectly. It's called Bhāsa, which loosely translates to appearance.
Appearance, right.
Yeah, it's that natural human tendency to look at the surface of something and just assume you're seeing the whole story. And you see a cup, it's just a cup.
Or you look at the back of your phone, the label says "Made in China," and you just accept that as the end of the narrative.
Exactly. You don't look any further.
Right. But to break the spell of that magic black box, we have to look closely at its literal surface, the glass itself, and start pulling the thread to see what unravels.
Yeah, crack the surface.
So let's crack the surface. Moving past just the appearance brings us to what the text calls a Bhāsa, or intimation.
Which is such a cool word for it.
It is. It's the moment you get that first tremor, that first realization of how vast this object actually is.
And the glass is the absolute perfect place to start. Because when you tap the screen of the phone in your hand, you aren't touching ordinary window glass.
Definitely not.
You're almost certainly touching Corning Gorilla Glass, which was originally formulated in a lab in New York. But what makes it so tough isn't just the raw material, it's the intense chemistry.
Okay, let's unpack this.
Yeah.
Because I've dropped my phone on concrete, more times than I can count, and it usually survives. How is a tiny piece of glass doing that?
Well, it comes down to a process called ion exchange. They take aluminosilicate glass, which is already quite strong.
Right, strong to begin with.
Yeah, and then they submerge it in a bath of molten potassium salt at 400 degrees Celsius.
Wait, molten salt, like a liquid salt bath?
Exactly. And here's why they do it. If you look at the surface of normal glass at an atomic level, it's full of sodium ions.
Okay.
But in that 400-degree bath, the extreme heat causes those sodium ions to literally leave the glass, and larger potassium ions from the salt take their place.
Oh, wow.
Imagine a microscopic grid, kind of like a chain-link fence, and you start forcefully stuffing oversized tennis balls into all the gaps.
It creates pressure.
Intense pressure. The larger ions pack the surface so tightly that it creates this deep layer of compressive stress. It's quite literally wearing chemical armor.
That is wild.
Yeah, that microscopic tension is what prevents a tiny scratch from propagating into a massive spiderweb crack when it hits the pavement.
But the wild thing is the raw silicon inside that highly engineered glass started its life as ordinary sand.
Yeah, just dirt.
Probably scooped out of a quarry on a completely different continent, and we're literally just on the outermost millimeter of the phone.
We haven't even gone inside yet.
Right. When you go deeper to the brain of the device, the main processor, it gets even more complex.
The processor is where the division of global intellectual labor becomes really apparent.
Okay, right, because most of these processors, whether it's an Apple chip or a Snapdragon and an Android, they're designed by teams in California.
Yep, Silicon Valley.
But they are built using an instruction set architecture from a company called ARM, located in Cambridge in the UK.
That's right.
But what does that actually mean? If California is designing the chip, what is the UK architecture doing? Are they just like drawing different parts of the circuit board?
Not quite. Think of the architecture as the fundamental vocabulary of the chip.
The vocabulary?
Yeah. When an app on your phone tells the hardware to add 2 numbers or, render this pixel, The hardware has to understand what those commands actually mean in terms of electrical pulses.
Oh, okay.
ARM designs that vocabulary, the grammatical rules of the processor. So the American companies design the physical layout, that massive city of transistors.
Right.
But the UK company dictates the language those transistors use to talk to each other. Every time you swipe your screen, British logic fires off inside an American design.
But there is a massive logical gap here that I'm struggling with. The US is drawing the blueprint, right?
Oh.
UK is providing the language. But neither of them actually builds the physical chips.
No, they don't fabricate them at all.
You can't just email a blueprint to a random factory and get a working microchip back. So who takes that blueprint and makes it real? It can't just be one giant factory.
Well, what's fascinating here is that it brings us to one of the most astonishing geographic bottlenecks on the entire planet.
A bottleneck.
A massive one. The chip inside your phone is arguably the smallest physical thing containing the most concentrated global history. And it's practically all manufactured on a single island, Taiwan.
Wait, really? Just one island?
Specifically, the Taiwan Semiconductor Manufacturing Company, or TSMC, they fabricate over 50% of all semiconductors on Earth.
Half of them.
And almost all of the most advanced ones. A single island of 23 million people runs the manufacturing for half the world's electronic brains.
The source material mentioned that making one of these chips takes up to 700 separate steps, running 24 hours a day for 12 straight weeks.
Yeah, 3 full months for one batch.
What are they actually doing for 700 steps? I mean, you're just printing a tiny circuit, aren't you?
Printing is a good analogy, but imagine printing a skyscraper one atomic layer at a time.
Oh, wow.
The process is called photolithography. They take a wafer of pure silicon, coated in light-sensitive chemicals, and shine incredibly precise light through a stencil to harden a pattern.
Okay, so like developing a photograph.
Exactly. Then they wash away the soft parts, etch the exposed silicon with plasma, bake it, coat it in copper, polish it flat, and start the whole process over for the next layer.
And they just keep doing that.
They do this hundreds of times, building three-dimensional cities of transistors that are measured in nanometers.
And this all happens in those famous clean rooms, right?
Yes. Clean rooms that are 10,000 times cleaner than a hospital operating theater.
Wait, why do they have to be that clean? That sounds excessive.
Because the features they are carving are literally the size of a few dozen atoms. At that scale, a single speck of dust or a microscopic flake of human skin
is huge to them.
It's like a meteor crashing into Manhattan. It would completely obliterate the circuit. The air has to be continuously filtered, so that essentially no particulate matter exists.
Here's where it gets really interesting, though. Because TSMC, as advanced as they are, they can't do this alone.
No, they can't.
To do that photolithography, to shine that light and carve those microscopic cities, they rely on another insane bottleneck.
They do. They rely on a company called ASML, located in 𝗏𝗺𝗺𝗺, which is this small Dutch town with a population of only about 45,000 people.
Just a small town in the Netherlands.
Yeah, and ASML makes extreme ultraviolet or EUV lithography machines.
And they're the only company on Earth that makes them.
The only one.
Which raises the question, why do we need extreme ultraviolet light? Why not just use a regular laser to draw the circuit?
It basically comes down to the laws of physics. Regular light, even standard ultraviolet light, has a wavelength that is simply too wide.
Too wide.
Yeah, trying to draw a nanometer scale circuit with regular light is like trying to paint a microscopic masterpiece with a thick permanent marker. It's just too blurry.
Ah, so you need a finer tip.
Exactly. Yeah. Extreme ultraviolet light has a much shorter wavelength, giving you an ultrafine tip pen.
But the way they generate that light, I mean, it sounds like pure science fiction.
It genuinely does. Yeah. EUV light is absorbed by practically everything, including air, so this entire process has to happen inside a total vacuum.
A vacuum, okay.
And to create the light, the machine drops microscopic spheres of liquid tin and then fires a laser at them.
Wait, it shoots falling droplets of metal?
Exactly. It fires 50,000 laser pulses per second at these microscopic droplets of liquid tin.
50,000 times a second.
Yes, and it vaporizes them into a plasma that emits the exact wavelength of extreme ultraviolet light needed.
That is just, I can't even wrap my head around that.
And ASML only manufactures about 50 of these machines a year.
Only 50.
They cost $380 million each, and they contain over 457,000 individual components. The entire advanced tech industry relies on those 50 machines.
And here's where the metaphor of the global nesting doll really comes in, because that Dutch machine, that $380 million marvel, also relies on other countries.
Oh, heavily.
It needs the most precise mirrors ever made by human hands to bounce that light around, which come from Zeiss in Germany.
Yeah, and to give you an idea of how smooth those mirrors are, if you expanded one to the size of an entire country, the tallest mountain would be just a millimeter high.
Unbelievable. And then it needs the actual lasers to shoot the tin, which come from another German company, Trump.
Right.
And it needs the specialized photoresist chemicals to coat the silicone, which come almost exclusively from Japan. It's a machine within a machine within a machine, spanning 4 different countries, all required before your phone can even turn on.
It's an incredible nesting doll of human ingenuity. But as precise and sterile as this engineering is, vaporizing liquid tin in a vacuum.
Right, the absolute peak of technology.
It all relies on something fundamentally raw, ancient, and deeply messy.
The physical elements, the dirt and the rocks.
Precisely. The physical extraction of the materials from the earth. A single smartphone contains between 60 and 70 distinct elements from the periodic table.
That's massive.
That's over half of all the known stable elements in the universe sitting right there in your hand.
And pulling those elements out of the earth is a stark contrast to those sterile clean rooms in Taiwan.
A total contrast.
The battery, for instance, needs cobalt. And according to the source, roughly 73% of the global supply of cobalt comes from the Democratic Republic of Congo, specifically the 𝗀𝗃𝗄𝗏 province. And to be clear, we are not taking a political stance here. We're just impartially reflecting what the source observes about the supply chain realities. But unlike the automated robotic clean rooms, a significant portion of this cobalt is mined by hand, sometimes by the small hands of children.
Yeah, the source explicitly points out that deeply unjust and exploitative systems sit right alongside this brilliant human ingenuity. It is the physical reality of the power source in the device.
It sits on the exact same supply chain.
And that raw extraction is happening all over the globe. Take lithium, another crucial battery component. A huge percentage comes from the lithium triangle, where Chile, Argentina, and Bolivia meet.
Way up high in the Andes.
Yes, at 3,600 meters altitude. They pump ancient mineral-rich brine from deep beneath the driest desert on Earth into these vast turquoise artificial lakes.
And then what?
Then they just let the sun evaporate the water for months until a lithium-rich crust is left behind, and the environmental impact is significant, with shrinking lithium lakes. Meanwhile, in Indonesia, massive smelting operations are slowly carving away entire mountainsides to refine the nickel needed for modern electronics.
And in China, they are processing between 70 to 85% of all rare earth elements. Things like neodymium.
Right, and neodymium is a great example. If we connect this to the bigger picture, why is it in your phone?
I mean, I have no idea.
Because to hear a voice on a phone call, you need a tiny speaker. A speaker works by vibrating a diaphragm back and forth to push air.
Okay, that makes sense.
To do that fast enough and powerfully enough in a space the size of your fingernail, you need incredibly strong permanent magnets. Neodymium provides that magnetic strength. So this phone is essentially the most concentrated gathering of Earth's chemistry in the smallest possible form.
The juxtaposition is just wild. You have an ultra-sterile, multi-million-dollar laser machine in the Netherlands relying on raw elements pumped out of high-altitude deserts in Chile or dug out of the mud in the Congo.
It really is.
But wait, it leads me to a big pushback question. If we have 60 to 70 elements coming from dozens of countries, moving from a mine in Africa to a refinery in China to a laser in Germany to a clean room in Taiwan, who is actually in charge of this?
That is the big question.
Like, who is the CEO of the global supply chain making sure the cobalt from the Congo meets the Dutch machine in Taiwan on time?
This raises an important question, and it is perhaps the most profound realization of all. There isn't one.
No one.
No single entity oversees this. And the realization of that fact brings us to the third stage of perception discussed in the text, pratiti, or felt sense.
Felt sense.
Yeah, it's the moment you transition from looking at facts on a page to actually feeling the invisible web holding everything together.
The invisible workers. Because the essay gives these incredibly vivid snapshots of the people trapped in this web. There is a Chilean analyst standing by an evaporation pond at dawn, testing the brine and worrying about the local water table.
Right.
There is a software engineer in Bangalore, India, writing the auto-rotate function at 2 a.m. on a Tuesday.
Yeah, tapping into the physics of the phone's gyroscope so the screen knows when you turn it sideways.
Exactly. And then that exact code is later used by a farmer in Bihar to check the weather on a wider screen.
It's all connected.
There is the Taiwanese process engineer who hasn't slept a full night in years because the pressure of yield optimization, basically getting more working chips out of every silicon wafer, literally never stops.
And think about it. None of these people speak the same language.
No.
They will never meet. They don't even know each other exist. Yet they are the phone together. Their labor is combined right there in your pocket.
So what does this all mean? How does it physically move around?
Well, we have to consider the physical logistics that bridge those lives, the cargo ships. At any given moment, there are roughly 53,000 cargo ships moving across the oceans, quietly facilitating this massive exchange.
The scale of the shipping is so hard to wrap your head around. A single ultra-large container ship leaving Shenzhen, China, can carry over 12,000 standard shipping containers.
12,000? That's huge!
If they packed one of those ships full of smartphones, it could carry upwards of 240 million individual devices.
240 million.
That is more than the entire population of Brazil. The population of a massive country floating across the Pacific Ocean, operated by a quiet crew of maybe 22 people.
And once that hardware is finally extracted, refined, assembled, and shipped across the ocean, I mean, it's still just an inert piece of glass and metal.
Right, it's basically a fancy brick.
Exactly. It needs software to wake up.
Yeah.
The Android operating system, which runs on the vast majority of phones globally, is built on the Linux kernel.
Okay.
Linux was started in 1991 by a Finnish programmer named Linus Torvalds as a free hobby project in his bedroom. Today, that kernel contains over 28 million lines of code, contributed by thousands of volunteer developers from 180 different countries.
Software obeys no geography. WhatsApp, an app that connects billions of people daily, was written by 2 Ukrainian immigrants working in California.
So when you look at the entirety of it, the mining, the engineering, the shipping, the coding, how do you make sense of a system this complex?
To me, it sounds like a massive global symphony.
Oh, that's a good way to put it.
But none of the musicians can see or hear each other. They don't have sheet music. They definitely don't have a conductor. Yet somehow they're playing a perfectly tuned chord.
Yes.
But if no one's in charge, how does it not just collapse? What happens if one section of the orchestra just stops playing?
Well, this is the paradox. We saw exactly what happens during the global chip shortage a few years ago. It does collapse.
Oh, right.
Car factories halt, electronics become scarce.
Yeah.
Because it operates entirely on mutual need. The Democratic Republic of Congo did not sign a master treaty with Germany so that Taiwan could make a chip for an American company.
Right, there's no grand plan.
Coexistence here is not a warm, fuzzy, utopian sentiment. It is a cold, structural, verifiable fact.
Mutual need.
Yes, it is written into the physical composition of the object. Remove any single node, remove the 𝗵𝗿𝗺𝗆 chemicals from Japan, or the instruction architecture from Cambridge, or the cobalt from Katanga, and the phone ceases to exist.
It's also fragile.
It is a web held together by the simple, stubborn reality that no one nation, no one company, no one person can build this alone.
Which brings us to the final stage of perception in the text. Anubhav, or realization. And this is where it comes right back to you, the person listening to this right now.
Yeah, bringing it all home.
To truly hold this phone is to hold the weight of all of it. The weight of the Katanga mining district, the weight of the 3 a.m. cargo ship in the South China Sea, the weight of the Finnish programmer's late-night code from 30 years ago.
The crucial takeaway here is that none of those millions of people are separate from you. Their labor, their knowledge, their exhausted nights and brilliant breakthroughs are quite literally resting in your palm.
It's incredible.
Because you are entangled with this entire planet, the physical reality of a Congolese miner or a Chilean water analyst is deeply tied to the tool you use to live your daily life. The question of their flourishing is not charity, it is tied to our own flourishing. Every time you unlock that screen, it is a mirror reflecting your physical connection to the entire world.
It fundamentally changes how you look at the device. But, we've spent this entire deep dive tracing the physical hardware of the phone, the dirt, the glass, the microscopic cities of silicon, and the code inside it. But consider this. What about the invisible infrastructure that wakes up the second you actually use it?
You mean the network itself?
Exactly, the network. Because the phone doesn't operate in a vacuum. To send a single video or load a web page, Thousands of miles of undersea fiber optic cables crisscrossing the ocean floor have to pulse with light.
That's true.
Massive data centers in remote locations have to process that request. And those servers generate so much physical heat that they require millions of gallons of water and massive industrial cooling towers running 24/7 just to keep from melting down.
Wow.
So if the physical phone is this miracle of human coexistence, what is the physical weight of our invisible digital footprint? The environmental and physical toll of the cloud every time we send a text message today. It's wild to think about.
It is the next layer of the web, an entirely different, massive, physical reality hidden right behind a simple digital action.
Absolutely. And something for all of us to chew on. For now, I want to circle back to where we started. Pick up your phone one more time.
The magic black box.
170 grams, the weight of a sparrow. The next time you feel that weight in your pocket, I hope you feel the whole world sitting in there with it. Thank you so much for joining us on this deep dive. Keep questioning the everyday things around you, and we'll catch you next time.
Thanks for watching. Please like, share, and subscribe to this channel in all your circles. Also, please fill the Google form by clicking on the link given in the description section of this video on YouTube. We will keep you informed about the launch dates of your favorite courses. Thank you.